Next to the last chapter. And I'm gonna pick out some problems from version 1 and 2. And did you have any that we need to get to? Okay. So let's see. Skip a few, scroll down. Here we go. Let's do number 9. This is, I'm gonna keep track of my versions here. Version 1. Thanksgiving out already. It's being old. At 1 atmosphere, liquid water is heated above 100 degrees C. Okay, pressure is 1 atmosphere. Temperature is greater than 1. That's greater than 100. Okay. The delta S for surroundings for this process is delta S for the surroundings equals what? All right. Look at my brain is here. Yeah, that's what I thought. So I'm gonna put it over here, just as a reminder. When we're at 100 degrees of 1 atmosphere, that's the boiling point. And at every phase change, you're at equilibrium, which means that the delta S is 0. Well, actually, delta S total is 0. So if we're greater than 100 degrees here, then we have yeah, we're actually exceeding 100 degrees, and we're putting energy in to boil the water. Because if we're at 100 degrees, we're above boiling point. So that means we have to put energy in to make the phase transition. All right, that makes it endothermic. And that's delta H is positive. So if this is positive, then overall is negative. So this would be negative. Now, is that one of our choices? Less than 0. Yeah, less than 0. Okay, I'm gonna leave that there because we might need it. Let's look at number 10. At 1 atmosphere, liquid water is heated above 100 degrees. Okay, so delta S for the universe, and then in the authors of the text use delta S for the universe to mean delta S total. So delta S total is what we're really after. Under the same conditions as number 9. So the delta S for the universe then is, well, if we do, maybe they mean universe. Maybe they are saying universe. Well, in that case, we know what the answer is. Right? That's the second law of thermodynamics. So it has to be equal to 0. If this were total, I don't know what it is because we don't have the other factor. Remember, if we were saying delta S total equals delta S for the system, plus delta S for the surroundings. We know this one is negative. We know that one's negative. Then we can't say anything about this one because we don't know what that one is. If we were at the boiling point, yeah, this one would be exactly the opposite of that one and equal in magnitude. Because at the boiling point, this value is 0.
You put your answer is greater than 0 though.
Did I?
Yeah.
Oh. Well, let's check the conditions again. No, heated above 100 degrees. Okay. At equilibrium, we should expect that to be 0. Okay.
On here, it looks like, do you have this too? Are you looking at this thing?
Yeah. Let's say delta S system is positive because heat is added to the system, providing more possible states for the system. Okay.
You like,
Yeah, I sort of hedged my bets there. Delta S universe, it depends on the magnitude of delta S system. If delta S system is greater than delta S surroundings, then delta S is greater than 0. The universe is greater than 0. And the process is spontaneous. At equilibrium, they should be both equal, but as the temperature rises above 100, more energy is added to the system than is required for the position. Okay. The extra heat gives the system more possible microstates. So if we go back to the original system plus surroundings, we know this one's positive. We know this one's negative because we're putting energy into it. We're increasing its energy entropy. And I'm just saying that if we can assume that the system is greater than surroundings, then we can make a comment on this one to be greater than 0. But only if, excuse me. No, wait a minute. Am I reading it backwards? Oh, I put the wrong, yeah. Now the logic works. We're adding, actually above equilibrium, we're adding more energy than the system needs to maintain equilibrium, which increases this above that. This just needs a certain amount to get it into the gas phase. But we have to add more than is required in order for that to happen. So according to that logic, then the total or the universe should be greater than 0. All right. Number 11 is big. Should be pounds. Okay, which of the following is true? So each one of those answers is referencing by spontaneous. We mean what? Well, spontaneous means under given conditions, there's no intervention required. The process proceeds without outside intervention. Okay. Well, as written, it would proceed to the right. Yes, that's true. So the first part of statement A is true. B is false. It's going the wrong direction. C is false, going the wrong direction. So it's a toss-up between A and D. Simply because the reaction is going the wrong direction. It's not spontaneous to the left. It proceeds to the right. Okay, then we need to look at the reasons. So A says, increasing the temperature may speed up the reaction, but it does not affect the spontaneity of the reaction. Increasing the temperature changes the entropy of the reaction, so it will affect the speed of the reaction. It doesn't necessarily, but it may speed up the reaction, and it usually affects the spontaneity of the reaction. There must be exceptions. Otherwise, we wouldn't hedge your bets like that. But the best of those two is D. All right, let's see. How many more do I want out of version 1? I only had a few picked out of version 1, and then I think we'd go to version 2. There's some duplication also. 34, we're still in version 1. Okay. For this reaction, carbon dioxide and water, CO2, and water, is it a gas also? Yeah. And methane produces methane and oxygen. And the delta H under standard conditions is 803. Which is fine, will increase K. The question is, we want to increase the K. But what is the K? Let's see. Do I have that written correctly? Yep. Every term is going to be in the K because they're all gases. All right. So K is going to be methane, oxygen squared, CO2, and water vapor squared. Okay. What other relationship do we have? If we're looking for, okay, let's take a look at the answers. What will increase K? Increase K. At equilibrium, we would have to have more of one of these and fewer of these. Decrease the number of moles of methane. Well, if we decrease that, no, that won't work. So let's do this. A, B, C, D, and E. So A is out. Increase the volume of the system. If we increase the volume of the system is going to try to respond by making more moles of gas if the balance is there. We've got 1, 2, 3 here and 1, 2, 3. We've got equal number of moles on both sides. So volume change won't have any effect. How about increase the temperature of the system? Okay, if we increase the temperature, since our delta H under standard conditions is 803, that is positive. That means this is an endothermic reaction, right? So that means delta H would be on this side. It would be, so I'm using Le Chatelier. So if we increase the temperature, we're increasing this factor and driving the reaction that way, giving us more here. That'll do it. That'll increase the K. And all the above, none of the above, it doesn't work. That's the easiest way to rationalize this one. I think I went overboard, didn't I? Yeah. I actually went to, I forget the name of that equation. I didn't list it in there. It's on the tip of my tongue. And it's gonna stay there. Because I can't remember what it's called. 36. Consider the gas phase reaction. NO and 1/2 O2. These are all gases, so I'm not going to put the gas phase markers in there. And what else are we given? Delta 8 minus 56.91. Delta H. Delta H 0 equals minus 56.91 kilojoules. And the K is given as, at that temperature, it's 1.46 times 10 to the 6th. And this is under standard conditions too. Okay, what would be the effect on the amount of NO present if we compress the equilibrium system to a smaller volume while keeping the temperature constant? Well, that seems like it should be fairly simple, I would think. All right, since we don't change the temperature during the process, then it doesn't matter where this one is, right? On either side, it really doesn't matter. It would go on this side, though, if the temperature changed. But since the temperature doesn't change, we're only interested in the number of moles of gas. So we got 1.5 moles here and 1 mole here. Okay. So what would affect the amount of NO present by compressing the system? The amount of NO, if we compress the system, it's going to try to make fewer moles. So we're going to decrease this because it's going to shift the reaction that way, trying to make fewer moles of gas. So NO would decrease. By compressing the system. Yeah, that was pretty simple, actually. All right. 46. Okay. Given the following data, calculate the normal boiling point for formic acid. The normal boiling point is going to occur at equilibrium. Right, so let's put what we know up here. Formic acid. So we've got HCOOH, liquid. And it's going to gas. All right. Well, we don't need to write the rest of it up there. We want to calculate what is the normal boiling point? Okay. So what do we know about this system in terms of its boiling point? Well, if it's at equilibrium, then we know that delta S total is going to be equal to 0. Right? They may not help us, but we do know that. We also know that at equilibrium, if delta S surroundings is minus delta H over T, then delta S system just changes the sign. Right? Because if we add these two together, they have to be 0 at equilibrium. Okay. All right. We're going to need trying to interpret my own answer. Okay. We have to calculate. We've got the enthalpies of formation for these reactants and products. We also have the entropies. Right? So if we're going to calculate the actual delta H, because we need that value right there, then that's going to be delta H, since we only have one of each, delta H formation for the gas minus delta H formation for the liquid. Okay. So if we plug our numbers in, we have gas minus liquid minus 363 kilojoules minus a minus 410 kilojoules. So that's going to be, let's see, 7 is going to be a positive because this is going to be positive. So 7 and 6 and 10 is 47, right? 47 kilojoules. Okay. We may have to change the units on that, but I'm going to do this first. Okay, the delta S then would be similarly gas 251. That's joules. Joules per, well, actually, it won't be mole, it'll be joules per K. Because we have 1 mole. So we multiply 1 mole by that, and it cancels the moles. And this is minus 130.
It's 251.
Oh, 0.1. Okay. And this is 0.0 joules per K. Okay, so that's going to be what?
21.1.
121?
Right.
Yeah. Yeah, that's right. Joules per K. All right, if we're going to put these together in terms of let's see. Yeah, using this formula, since we're talking, these are system values. Right, so if we solve this one for temperature, let's put it over here so we can keep that as is. Solve that one for temperature, we have delta H over delta S for the system. Remember, if I don't write system, that's what it means. But we need the same units of measure. Right? So this would be minus 4, let's see, no, it would plus 47. This would be 47 times 10 to the third joules. Right? So this term right here would be 4.7 times 10 to the fourth joules. And this would be 121.1 joules per K. Right? Denominator is numerator. Joules cancel. Put K in the numerator. And we're in degree C, so we got to solve this one first. And it's 4.7. 104 and 121.1 divide. So this is going to be 388 K. And then we would subtract 273 from it, right? So I get 115 degrees C. Right? Yeah. It's 46. Multi-step problem. Okay. Do the next. 52. Okay. All right. We've got an equation here where we have water plus half oxygen. See, 52. Water, gas, plus 1/2 O2 gas is in equilibrium with hydrogen peroxide. Also a gas, yep. And the delta G is given as, no, that's what we want. The temperature is 600.1 K. Okay. So how are we going to get delta G? We need to be able to use this formula. I'm going to put it up here on the right. Equals negative log RT log K. Negative RT log K. Yeah. That's right. We just need to know what the K is. All right. So we got to find the K from this for this one from the given equations. Those are at, oh, we're going to take that T into account here. We're good. So we've got two equations. The first one has hydrogen peroxide on the correct side, so we can put that in. Plus O2, H2O2 gas, and this Kp equals 2.3 times 10 to the 6th. So that takes care of this one. And then the second one has water on the wrong side. No, it hasn't. Yeah, it's on the wrong side. So we have to flip it over, but we have to take half of it because we only need one water on this side. And that's equal to 2H2 plus O2. These are gases. Okay. So we got to take, this was 2, wasn't it? Yep. We got to take half of this one, half of this one. And what does that do to the Kp? Take half the Kp, don't we? No. Square root of. So we're starting out with Kp of 1.8 times 10 to the 37. Okay. So that takes this one down to 1, takes this one down to 1, takes that one to a half. And this one then would be Okay, so if we add these together, we've got this half cancels half of that one. So we're good there. And that one goes and leaves us with a half here. Right? And then this H2 is canceled by this H2. And that water is checked with that. I think we're good. Okay, so what do we do with the K's? Multiply them, don't we? Yeah, we'll multiply them. So we multiply this square root of this K times that K, and that gives us the overall K. Where's my key? There it is. And then 3, 6. So you get in the 24th. No. Wait a minute.
Doesn't look like you squared 1.8 yet. It looks like you squared 5.56 times 10 to the negative 38, but I don't know how you've gone.
Wait a minute. Be sure I did it right. Oh. We flipped the equation. Okay, so we have to take the inverse of this and then take the square root. All right, let's try that one again. I hit the inverse key, then take the square root. Right. Then times 2.36. There we go. 5.42 times 10 to the minus 13. Okay. All right. Well then, delta G0 equals negative, R is 8.2, 3145. Temperature is already in K. And then natural log of 5.42 times 10 to the minus 13. There we go. And then take natural log times. So I get 1.41 times 10 to the 5th. Units of measure. Joule. And our answers are in kilojoule, right? So it'd be 1.41 times 10 to the second kilojoules, or 141. Okay, this is taking longer than I hoped. Let's see. 53? Yeah, 53. We did 52. Now 53. So we got NO2 dimerizing to N2O4. And we're given delta H0 negative 56.8 kilojoules. And delta S0 minus 175. Minus 175 point nothing joules per K. In the container at 298. 298 is yeah, that's 25 degrees. That's standard conditions. 298 K is standard conditions. N2O4 and NO2 are mixed with initial partial pressures of 2.4 and 0.42, respectively. Okay, N2O4 is 2.4. And NO2 is 0.42 atmospheres. Okay. Which of the following is correct? Some N2O4 will decompose, some NO2 will dimerize. System is at equilibrium. All right. We got to be able to calculate. We got to compare Q with K. So in order to do K, I combined two equations, didn't I? Yeah. Okay. We're not given delta G here. And if we had delta G, we could do this one and find out what the K is. But we don't have delta G yet. So delta G equals delta H minus T delta S. And if we combine that with this one, and these are all standard conditions, combine it with this one, then we can say if this delta G is equal to that one, then this expression is equal to that expression. Okay, and we can solve for natural log K. That'll get us part of the way there. Divided by minus RT. Okay, so we can plug in minus, let's see, this has to be in joules. Right. So we need a negative 56.8 times 10 to the third joules. Minus temperature is 298 times delta S minus 175. Okay, this is K. Okay, divided by R 8.3145 and temperature 298. Okay. Okay, that should give us the natural log of K, and then we can find out what K is. All right. So if I did this right, negative 21.05 is log K. So K is going to be the anti-log of this value. So I just need to hit e to the x for natural log. This is 7.23 times 10 to the minus 10. Here's the K. So far, so good?
I
No,
think so.
no, that's not right. What did I do wrong? Minus? Okay, that's good. 75, 298. That should be a positive. And 83145, 298. Okay, so I set it up right. Must be a calculation error. Let's go back and do that again. This time, I'm going to do it piece at a time. This one is a positive. 5215 times 10 to the 4. 5.21. Okay, so that's going to be plus this one. Let's change the sign. No, wrong. Okay, that's positive, so I can add those together. All right, so this whole thing up here is negative 4.65 times 10 to the third. And divided by this negative. So this is going to be a positive. It was a calculator error. 8.3145 and then 298. So this one down here, negative 2.478 times 10 to the third, divided into that one. Now we're talking 1.8767. And then I do e to the x. This is 6.53. Does that agree?
Yeah.
Okay. So now what we need is the Q. This is the K. We need the Q for that one. So the Q is going to be 2.4 divided by 0.42 squared. Dang it, 13.6. So Q is greater than K. That means coming back this way, right? Yeah, N2O4 will decompose into NO2, headed this direction. This is greater than that. Okay. Calculators are great when they work. We're going to get out of chapter 1. Not yet. 56. I mean, not chapter 1, but version 1. This system, PCl3 and chlorine. PCl3 and chlorine is in equilibrium with PCl5. I'll bet money. And the delta H0 is equal to minus 92.5 kilojoules under standard conditions. If the temperature of the system is raised, the ratio of partial pressure of PCl5 to partial pressure of PCl3. Okay, partial pressure, the ratio of the partial pressure of PCl5 to 3. So this is what we're looking for. Partial pressure of PCl5 divided by PCl3. We want to know what that's going to do, up or down or stay same. If the temperature of the system is raised, all right, so if this is a negative, this is exothermic, that means it's on this side, right? Okay, so if we raise the temperature, we're going to increase this value, excuse me, we're gonna decrease that value because it shifted to the left. We're gonna decrease this one and increase this one. So the ratio should decrease, right? Yep. I like simple problems like that. All right. Let's see. All right, so it's gonna 58 and version 256 must be related. Yeah, so we'll do 58 here. Then we'll migrate to the 56 in version 2 and use the same information. The equilibrium constant for the dissociation reaction of chlorine to two chlorine atoms. And this has to be gas. Was measured as a function of temperature in K. Graph of natural log Kp versus 1/T for this reaction gives a straight line. Oh, okay. So what we're saying is natural log Kp versus 1/T. So which one goes where? One over T goes down here. Okay, versus 1/T. Natural log Kp. And it looks like the slope is negative. And the slope is equal to minus 1.651 times 10 to the fourth. And the intercept is 1451. So this is 14.51. Okay, we're given all that information. Okay. From this data, which of the following statements is true? Exothermic, endothermic, rate is high, reaction is not spontaneous. All right. What we're looking at is this equation. Yeah. Y equals M is minus delta H over R. Minus delta H over R. Y equals mx plus b, which is delta S 0 over R. Okay, there's our equation. And we want to answer which of these is true. Well, exothermic or endothermic, we need to know this value right here, delta H. So if the slope is negative, if this whole thing is negative, then delta H has to be positive. Right? So this is endothermic. Okay. Now B works. Can we tell anything about the reaction rate? No, because we're talking about equilibrium. This is thermodynamics. It's not kinetics. Okay, so we have no information about the reaction rate. How about spontaneity of the reaction? Well, in order to do the spontaneity, we need to be able to calculate delta G. All right, so if, did I go that far? That stopped at endothermic, didn't I? I'm curious. All right, can we say anything about this one? We don't know log K. We don't know K from this one. Okay, so I think I'll stop while I'm ahead. Let's go to 56 in version 2. Maybe that's where we pick it up again. '56 in version 2. Okay. 56 version 2. So version 2, number 56. Question is, the equilibrium constant for this was measured as a function of, okay, that's same if we've already got that. The value of delta H for this dissociation reaction is, well, delta H, we know that this expression, the slope minus 1.651 times 10 to the fourth is equal to negative delta H over R. Right, so R would be brought over here, which would be 8.3145 times this value equals negative delta H. Let's see, 1.65. So I get delta H 0 equals 1.37 times 10 to the fifth joules, or 1.37 times 10, let's clean that up, times 10 squared kilojoules, or 137 kilojoules. Be close enough. But it's positive because that's negative and this is negative, so delta H has to be positive. All right. So we'll go back to where were we? 58. Oops, too far. That may be the last one. No, 59. We'll do 59 in version 1, and then we can go to version 2. Arrhenius. It's the Arrhenius equation. Okay, 59. For the process at 300 K, delta G is minus 10.4 and delta H is minus 7. If it's carried out reversibly, the amount of useful work that can be performed. The amount of useful work that can be performed. So we need oh. Delta G is given, right? The amount of use, if it's carried out reversibly, that means you get the maximum amount of work. And if delta G is negative 10.4, that is the maximum free energy available. So that's minus 10.4. That's 10.4 kilojoules. Okay, that's kind of a trick question. Now, if not carried out reversibly, you get less than that. All right. So let's take a look at version 2. Oops. There we go, number 2. Here on time. You stepped an hour. Oh, okay. So far, so good. A 2-bulb flask contains 5 particles. What's the probability of finding all 5 particles on the left side? All right, so we got this bulb connected to another bulb, and we're going to have 5 particles in here. A, B, C, D, and E. What's the probability of finding them all on that side? There's a formula. No, it's not that one. Okay. I sort of approached it from the ground level. What's the probability of finding one particle either here or there? It's 1/2, right? It's either there or it's there, 50%, half. Okay, what's the probability of finding the other particle over here or there? It's another half. All right, so we have that 5 times, which is 2 to the 5th power. So that's 4, 8, 16, 32. So what's 1 divided by 32? Well, if we do our calculations, it should be 3.13%. That's the probability of finding all 5 on one side. Okay, let's see. How about skip a few? There we go. Number 14. For this process, CHCl3 is chloroform, I think. Trichloromethane, solid, and we're going to liquid. Okay, and the delta H0 is given as 9.19 kilojoules per mole, and delta S0 equals 43. It's positive also, 43.9 joules per K mole. What's the melting point of chloroform? So that I don't waste your time and mine both. Okay, we did one kind of like this earlier, didn't we? If we're at the phase change, that means delta S total is equal to delta S surroundings plus delta S system. And if this is 0, then these have to be equal and opposite. Right? So we can use this one for the system because that's the temperature we want. What is the melting point? So delta S equals delta H over T, and then T would be delta H over delta S. Under standard conditions. Right. So delta H needs to be converted to joules. 9.19 times 10 to the 3rd joules per mole. And then 43.9 joules per K mole. So moles cancel, Joules cancel and we're left with K. And I get 209, that's close enough. K, is it in C? Yeah. Minus 273. Which is minus 63.7, 64, close enough. This is the melting point for chloroform. All right. Okay, next. Number 20. In which case must a reaction be spontaneous at all temperatures? Okay, so here we're looking at Gibbs equation. Okay, and what sign would delta G be for spontaneity? Negative, right? So this has to be negative for a spontaneous reaction. Okay, what would give you negative under all at all temperatures? Well, this would have to be positive, and this would have to be negative. So an exothermic reaction with an increase in entropy. All right, so delta H would be negative delta H D. Delta H negative, delta S positive. D would be the answer. '26. Starting to give out on me too. These have any life left in them. When a stable diatomic molecule spontaneously forms from its atoms, what are the signs of delta H, delta S, and delta G? Okay, a stable diatomic molecule forms from its atoms. So we've got a diatomic molecule, and these, we have to be gas. We have two X's over here, like that. That's our equation. Spontaneously forms. If it's spontaneous, let's see, we've got delta H, delta S, and delta G. There. If it's spontaneous, that has to be negative. Okay. If we're going from two atoms to only one molecule, then this delta S is decreasing. Right? Okay. And if we're making a bond between these two free atoms, they give up energy when they do that, because the bond makes them more stable. So this is going to be negative also. They're all negative. Okay. Right. Next. 31. Calculate solubility product for the salt sodium chloride at 25 degrees. Okay. Brain here. Oh. Okay. Solubility product is written as sodium chloride, solid goes to sodium ions and chloride ion. We're looking at SP. Okay. The clue here is we're given delta G of formation for each one of these. So if we want to find out what's the delta G for the entire, for this whole process, we would say delta G equals delta G of reactants minus delta G, products. Products minus delta G of reactants. So that would be sodium delta G is minus 262. And this is kilojoules minus 262. And then we've also, let's see, minus 131, minus 131. And then minus whatever delta G for the reactant is, which is minus 383.8. That's 383.8. All right, so this is going to be in kilojoules. And 383.8. So I get minus 9.2 kilojoules is the delta G of that reaction. All right, we're still looking for K. So if we go to this expression here, there's our K, right? Delta G, and this has to be in joules. So it's minus 9.2 times 10 to the third joules equals minus 8.3145, and temperature would be standard conditions 298 K, and then log KSP. Okay, so log of KSP equals this one divided by that product. All right, and 8.3145 to 8 and divide this. Okay, so this one is 3.713. And KSP then would be e to that value, which would be 40.98 or 41.0, 41. Yeah, 41. Okay. Stop me if you have questions. You're awful silent. It is a Monday morning. 34. Oops. All right, gas phase reaction. If the system equals how will raising the temperature affect the amount of NO present? We did one like this before. Gas. Oh, we did one where we combined equations to get this one. In equilibrium with NO2. Okay, and the delta H is minus delta H is a minus 56. So it's going to be on this side. Minus 56.91 kilojoules. Right, exothermic. And the K is 1.46 10 to the sixth. At 25 degrees. Okay, that's everything given. For this system at equilibrium, how will raising the temperature affect the amount of NO present? We raise the temperature. Oh. We raise the temperature, it will increase the amount of NO. Yeah. Right, because this is a term, delta H. If we add more of that, we shift it back this direction and increase that, Right. Let's see, what about, oh, the second law of thermodynamics states, for the entire universe, entropy is always increased. In other words, the universe is running downhill, so to speak. That was simple enough. How about 42? A mixture of hydrogen and chlorine remains unreactive until it's exposed to ultraviolet light from the burning magnesium strip. Then the following reaction occurs very rapidly. Okay. So we get hydrogen plus chlorine gas in a container. And they're just sitting there until we add a little energy. We add activation energy. And that makes 2 hydrogen chloride gas molecules. Okay. Which of the following is consistent with this information? Well, let's see. A, B, C, D, and E. A says what? The reactants are thermodynamically more stable than the products. Well, delta G is negative, right? So that means the reaction to the right is spontaneous. But does the experiment itself tell us that? With this extra information, we can make that, we can draw that conclusion. But based upon the introduction of ultraviolet light to this reaction to meet the kinetic needs, right, the activation energy, then we're going to say that this is hydrogen gas and chlorine gas are kinetically stable. The reaction is spontaneous, right, because delta G is negative. We can say that. But if we add the ultraviolet light, that supplies kinetic energy, that supplies activation energy to the reaction. So the reactants are thermodynamically more stable than the products. Well, no, thermodynamically more stable? No, because it's spontaneous reaction. So this is more thermodynamically stable. All right, so A can't be it. Then B, the reaction has a small equilibrium constant. A small equilibrium constant. Well, we would have to introduce it into this situation here. If it was negative 45,000 divided by 8, which is roughly take it down to 4,500 or 500, 5,000 divided by a temperature of 200 would be about, I don't know, 40. And then log K Let's see. I'm just, getting in the neighborhood. No, it's very large. It's like 10 to the 17th. All right, so that can't be it. Ultraviolet light raises the temperature of the system. Ultraviolet light doesn't do anything but supply activation energy. It doesn't raise the temperature of the system. The negative value for delta S slows down the reaction. Well, we covered that one earlier, right? Any thermodynamic term says nothing about the rate of the reaction. So E, by process of elimination, E should be a good answer. Reaction is spontaneous, yes. Negative delta G. Reactants are kinetically stable. Yeah, because they don't move until we give them the activation energy. Right. Okay. That's a long way around the barn, but we got the answer. All right. Skipping a few, come down to 52. Looks like Arrhenius again. Equilibrium constant of a certain reaction was measured at various temperatures to give the plot shown below. What's the delta S zero for the reaction? All right, I'm not going to redraw that one. We're looking at this equation right here. And if we're after delta S, we want the intercept, the y-intercept. So that says that delta S over R is equal to 3, right? The y-intercept is 3. Okay, so delta S 0 equals 3 times 8.3145. So in the neighborhood of 25 C. Okay. All right. 56. We did 56. All right. Thank you. Waste any time on that one. 57. For a certain process at 300 K, delta G is minus 12.2 and delta H is minus 7. The process is carried out so that no useful work is performed. Delta G is, well, delta G is still minus 12.2. It doesn't matter what you do with it, right? Delta G is delta G. That was simple enough. Oh, that's it.